What if the reality we perceive is only half the story? What if particles, those tiny entities that make up the universe, have a dual nature, acting not just as particles but also as waves? This idea, as radical as it might seem, is not a product of science fiction, but a revolutionary concept that emerged from the mind of Louis de Broglie in 1924. In the early 20th century, de Broglie proposed a mind-bending idea, the concept of wave-particle duality. He suggested that all matter, even particles like electrons and protons, exhibit wave-like properties. This was a daring inversion of the established idea that light, traditionally considered a wave, could exhibit particle-like behavior in the form of photons. De Broglie simply asked, if light can act like a particle, why can't particles act like waves? The cornerstone of de Broglie's theory is the concept of the wavelength of matter. According to his hypothesis, every particle has an associated wavelength known as the de Broglie wavelength. This wavelength is inversely proportional to its momentum and directly proportional to Planck's constant, a fundamental constant in physics. De Broglie's wavelength can be calculated using a simple equation, lambda equals h divided by p, where h is the Planck constant and p is the momentum of the particle. This equation reveals a fascinating insight. Particles with greater momentum have shorter de Broglie wavelengths, suggesting a more particle-like behavior. But how can we be sure that particles behave like waves? The answer lies in the realm of experimental physics. The wave-like behavior of matter was confirmed in various experiments, such as the Davison-Germer experiment. In this experiment, electrons were diffracted by a crystal lattice, producing interference patterns consistent with wave behavior. The concept of de Broglie matter waves has had wide-ranging applications. It has been essential in understanding phenomena such as electron diffraction and electron microscopy. It has also provided insights into the wave-like behavior of particles in quantum systems. But perhaps the most profound impact of de Broglie's hypothesis has been on the field of quantum mechanics. His idea was pivotal in the development of quantum mechanics, influencing the wave equations formulated by Schrödinger and others. It helped reconcile the classical mechanics of particles with the probabilistic nature of quantum mechanics, bridging the gap between the macroscopic and microscopic worlds. In conclusion, the idea of de Broglie matter waves proposed a fundamental duality in nature, revolutionizing our understanding of the behavior of particles at the quantum level. It laid the foundation for the wave-particle duality principle, which is central to the field of quantum mechanics. Through his daring hypothesis, de Broglie showed us that the reality of the quantum world is far more fascinating and complex than we could ever have imagined.